Usually speaking, substances are going to exist in one of three phases depending on the temperature: solid, liquid, or gas. Usually, right? We're not going to talk about plasma or Bose-Einstein condensates, of course. We call states of matter phases, and when we move from one phase to the next, that would be a phase change. So with solids, liquids, and gases in mind, let's first talk about those phase changes that require energy. First is the phase change from solid to liquid that we simply call melting. Remember that solids are held in place by intermolecular forces. They have some vibrational energy, but not a lot of other motion. When we heat that substance, when we introduce more kinetic energy, those particles can begin to move a little bit more and finally maybe break away to where they have fluidity. They become liquids. The temperature at which you can have a solid phase and a liquid phase existing together is called the melting point. It's the temperature at which the forces that are holding that crystal lattice structure together are being broken, converting that solid into liquid. Interestingly, if I have a solid and I'm adding kinetic energy to that solid, i.e. heating it, the temperature will increase until I get to that melting point. When I get to the melting point, the temperature will level off. It will stop increasing. Now, I'm still adding kinetic energy in the form of heat, so energy is still being added, but the temperature is not rising. Why is that? Because it's during that melting phase in which you're overcoming all those intermolecular forces, allowing that solid to become a liquid. And after that, if you continue to add energy, the temperature will indeed increase. If you continue to add energy in the form of heat, you'll arrive at our second phase change, which is called vaporization. That's the change between liquid phase, of course, and the gaseous phase. So as we add kinetic energy to that liquid, we add enough kinetic energy to where those particles move much further apart and much faster, giving us a vapor. As we saw with the melting point, when we arrive at the boiling point where vaporization occurs, the temperature again will stop increasing. Instead, the energy will be used to overcome those necessary intermolecular forces to convert that liquid into a gas. Once it becomes a gas, and if you continue to add kinetic energy, the temperature will begin to increase again. Vaporization can occur at the surface of a liquid. We call that evaporation. Even at cold temperatures, some water molecules have the ability to evaporate, to achieve that gaseous phase. Remember that we have air molecules all around us that give us that atmospheric pressure as they collide with our particles and collide with the particles inside this beaker. But as we indicated, there is some evaporation that occurs at the surface of this water. So because of that, we have what's known as vapor pressure. Little particles of water that are colliding with the particles of air around it. The collisions of those water molecules provide pressure. So again, vapor pressure is the pressure that's exerted by a vapor over the surface of a liquid. As we get closer and closer to that vaporization stage, we give those vapor particles enough kinetic energy to where the vapor pressure begins to equal that of the atmospheric pressure. When that happens, we arrive at what we call the boiling point. At the boiling point, you have molecules throughout that liquid that have achieved vapor stage. Because of that, you'll have bubbles of vapor that form, and they collect below the surface of the water and make their way very rapidly to the surface. The last phase change that requires energy is what we call sublimation. This is the phase change occurring from the solid state to the gaseous state. During the sublimation process, that phase change occurs without going through a liquid state. Carbon dioxide is a very common substance that does this. Under ordinary circumstances, we can have what we call dry ice, which is solid carbon dioxide, and that dry ice you'll find will sublimate. It will move directly from the solid phase to the gaseous phase. Now let's talk about the phase changes that release energy. The first phase change is that of freezing, where we move from the liquid phase to the solid phase. During freezing, those particles in that liquid would begin to slow down. They begin to give up some of that kinetic energy they've had, and when that happens, the intermolecular forces begin to take hold a little more until finally they reacquire that rigid solid state. Freezing, of course, is the reverse of melting, and the freezing point is that temperature at which a liquid is converted into a solid. Now, as we said previously, there is a release of energy that happens in freezing. This is why in some areas of the country, farmers that have fruit trees may use water sprayers on their crops when it gets cold at night. If the temperature is going to dip down below freezing, they'll spray those trees with water. The water collects on the fruit, and as the water freezes, there is a release of energy that happens. Where does it go? Into their surroundings. What are they surrounding? The fruit. The fruit is able to absorb that energy then and protect it from freezing. The second type of phase change that releases energy is called condensation. It's when we have the gas phase moving into the liquid phase. As we saw with freezing, when condensing occurs, those gas particles move with less kinetic energy to the point where the velocity decreases, which allows for intermolecular forces to take hold. Condensation is, of course, the reverse of vaporization. Rain and clouds, fog, they all come from condensation. If you have warm, moist air that passes over a region of cooler land or cooler water, it's going to cause a decrease in that kinetic energy, which will drive the condensation to occur. The last phase change is going from the gaseous phase to the solid phase. We call this deposition. One example of this may occur in the wintertime. If you have water vapor in the air and it makes contact with an extremely cold window, say a below freezing day, you'll have frost to form. That's an example of deposition. Deposition, of course, is the opposite of sublimation. We can actually illustrate the relationship between pressure and temperature for a substance by use of what we call a phase diagram. It's simply a graph of pressure versus temperature, and it shows in what phase a substance will exist based on certain conditions of pressure and temperature. Here's an example. This is the phase diagram for water. You can see to the far left the region that is the solid region. The combination of pressures and temperatures in that region will lead you to have solid H2O. On the bottom and far right side, we have the gaseous phase. Any combination of pressure and temperature that falls within that range will give you the gaseous phase, or water vapor. In between that, we see the liquid phase. The line that separates the solid phase from the liquid phase is known as the line of fusion. It demonstrates the melting point or freezing point depending on the direction you're going. And as you can see, that melting point or freezing point may change based on different conditions of pressure and temperature. The same can be said for the line between the liquid phase and the gaseous phase. That's known as the vaporization line. And finally, that third line that occurs between the solid phase and the gaseous phase is known as the sublimation line. As you can see, we have a point at which all three lines come together. That point is known as the triple point. It represents the temperature and pressure at which all three phases can exist simultaneously. So all 6 of our phase changes can occur at that triple point. That's pretty remarkable. The other point worth mentioning is up near the top here, and it's called the critical point. The critical point shows us the critical pressure and critical temperature. So if you have H2O at 374 degrees, it means that no amount of pressure exerted on that sample will cause it to become liquid, as long as it's above that critical temperature. This is a heating diagram for a typical sample of water. You can see that at the beginning we are in the ice phase, or the solid phase, and as we add energy, going from left to right, the temperature will increase in that sample until we get to the melting point, 0 degrees Celsius. Notice that the temperature flatlines at that point because all the energy that's being added to that sample is going toward overcoming those intermolecular forces, converting from solid to liquid. Once that happens, at the end of that flat line, you see the liquid phase begin, and the temperature will begin to increase as you add more energy. That amount of heat that converts the solid to the liquid is called the heat of fusion. And that amount of energy will be same whether you're going from solid to liquid or liquid to solid. You'll either gain that amount of heat or release that amount of heat as you go from liquid to solid. The temperature will continue to rise while it's in the liquid phase until we get to the boiling point. Again, you can see it flatline while it's being converted from liquid to gas. The energy that's involved in converting that liquid to gas is called the heat of vaporization. As you can see, the heat of vaporization is considerably more than the heat of fusion. It takes a lot more energy to convert from a liquid to gas than it does to convert from solid to liquid. That's all we're doing for today. In this video, we talked about phases and phase changes. We discussed phase changes that require or absorb energy in the process and phase changes that release energy in the process. We also showed an illustration of a phase diagram in which we can see what phase a substance will exist depending on the particular conditions of pressure and temperature. Congratulations on completing another chapter. In our next chapter, we'll talk about gas laws. So until next time, God bless.